What's up, everybody? Welcome back. Today, we're talking about equilibrium. That's right, today's equilibrium lab. So, what is equilibrium? Right? What is equilibrium? When we talk about equilibrium, we have to know about reversible reactions, and it's exactly what they sound like. It's reactions that if you take A plus B gives you C plus D, for example, it's possible that also C plus D gives you A plus B. Equilibrium, reversible reactions, right? So we can go back and forth, and depending on the conditions, right, we can make more of C and D, or we can make more of A and B. And guess what? Sometimes we hit the conditions where we're making A and B at the same speed as we're making C and D. And that is equilibrium. When the rate or speed of making the reactants is the same as making the products, right? So reversible reactions, these reactions, they do not go to completion. So A plus B do not completely make C plus D, because as we make C plus D, it makes more of A and B, right? So most of the reactions that we see in nature, especially the reactions that happen in our bodies, they are reversible. They go back and forth, back and forth. You want to make things and then use the things that you made to make the original things if you need them. It's actually a very clever way to recycle stuff, right? So, physical equilibrium is when you're dealing with physical things, things dissolving, right? And it can also go back and forth. But dynamic equilibrium, right? Again, the dynamic equilibrium is this one I was talking about, where the forward reaction is equal and opposite to the reverse reaction, right? But one thing to note is it's not, when we're talking about these types of equilibrium, it is not the amount. So, first of all, this is reversible. So A plus B goes back to C plus D, right? So we need to know that it is not the amount of reactions, is the rate, is the speed of the formation. Big, big difference. So here, right, as you can see, again, this is a reversible reaction, right? So the forward reaction, right, where you are making C and D, and then the reverse reaction. So the rate or the speed of the disappearance of the reactants goes this way. And then the speed of the appearance of the products goes this way, right? Not the product, the appearance of the reactants. So the reverse reaction. So you have the reverse reaction and then the forward reaction. They will get to a point where these rates, these speeds are equal. That's when you reach the chemical equilibrium, right? This is a dynamic equilibrium. And again, the concentration of the reactants and products is not equal. At equilibrium, the concentration of the reactants and the products is not equal. You have to remember that. It's the rate. It's the rate or the speed of their formation is equal, but the amount itself is not equal. You have to remember that. But that is, in a nutshell, what a chemical equilibrium is, right? And again, it happens all the time in the lab, in the body, in nature. We love reversible reactions, we love equilibrium. But with that being said, as I mentioned earlier, right, conditions are going to determine whether this reaction goes is bigger than this, right? So big arrow, small arrow, or if it's the opposite, right? So At equilibrium, we're going back and forth at the same rate. But in a lot of conditions, you will have you will not be at equilibrium. You will be making more of this compared to this or the other way around, right? So we need to learn and know what are the conditions that are going to change equilibrium and why does it is it even going to change, and more importantly, how will the equilibrium react if you change the conditions. This takes me to Le Chatelier's principle. So this principle of Le Chatelier is telling you that if a stress is applied, if something is changed to a reaction at equilibrium, right, then the net reaction is going to try to relieve or remove that addition, to relieve that stress. It's a very important concept, right? So, this we're going to talk about it in terms of concentration, in terms of pressure, in terms of temperature. But to kind of give you an overview, this is how it looks like, right? This is how it exactly looks like. So, let's say, let's look at it in a real example. Right? So let's say, okay, Na plus mm, MgCl2 going to be equal to this would probably wouldn't be reversible, but you never know. Magnesium plus NaCl, right? So this is a nice little reaction, right? So let's say I say that this is a reversible reaction, right? Now think about it this way. What if I add NaCl, salt, to this reaction? I pour NaCl to that reaction, right? If I pour NaCl to this reaction, right? This is in at equilibrium. So they tell you this is at equilibrium, but I add NaCl. Think about it this way, right? If we add NaCl, we have increased this amount. We have increased this amount. And this principle, Le Chatelier's principle, tells us that the reaction will react by minimizing, taking away that stressor. So the question will be, which direction will the reaction go? So if we're making too much NaCl, guess what? We're going to go in a direction that gets rid of it. Which reaction? It's this way, right? We're going to go this way. So the reaction in this case will go to the left. Le Chatelier's principle. If you add something, you add a stressor to an equilibrium, to a reaction at equilibrium, the reaction will adapt by trying to remove that stressor, by going in a direction that removes that stressor. So that means that, for example, if we add sodium, guess what? It's going to go that way. It's really cool. It's really, really cool. And guess what? This is actually another interesting thing about it, because as I was saying, it's not just the temperature. No, it's not just the concentration. You can use the temperature. So let's say you have something like CH4 plus O2 is equal to H2O plus CO2. This is a combustion reaction, right? But this probably exothermic reaction. An exothermic exothermic reaction. What does the exothermic reaction do? It gives away heat, right? Gives away heat or gives away energy, right? So if it gives away energy, I want you to think about it a little bit, right? If it gives away energy, if it gives off heat, then if this reaction is at equilibrium and I heat up the reaction, I increase the temperature, how is it going to react? If it already gives off heat, and then we increase the temperature, then it's not going to keep going this way, is it? No, because then it will increase the heat. No, we want to reduce the heat, so it's going to go this way to reduce the heat. If it's exothermic, right? Makes sense. But guess what? If it's an endothermic reaction, it's going to be the opposite, right? So let's see what I have here. So I have a few scenarios here where, like, if you have an equilibrium, right, at equilibrium here, but you increase the reactant. So you increase the reactant. This is a good visual actually. You add the reactant here, you increase the reactant, then it's going to shift to the right to return the equilibrium. So it's going to go that way, right? I'm looking at a different thing. It's going to go this way, right? It's going to go this way to shift to the right, right? So it's going to add more so that we shift to the equilibrium, right? So if you increase the concentration of the product like we did earlier, then it's going to shift to the left, right? This is what I was showing you here. Now, another thing, again, like I said, for an exothermic reaction, right, the heat is released, meaning that if you increase the heat, we're going to shift to the left to remove that heat, right? And then if you decrease the heat, it's going to shift to the right to increase the temperature. But that's the exothermic reaction. An endothermic reaction is going to be the opposite, right? If you add heat, it's going to shift to the right. It's going to shift to the right this way, right? No, my camera is flipped. But yeah, it's going to shift to the right that way. This way, yeah, on your side, right? Basically, an endothermic reaction needs to add heat into it, right? So if you increase the heat, it's going to go this way so that it can keep reducing the heat, right? Whereas an exothermic reaction is going to go that way because the heat is produced, right? So that is Le Chatelier's principle in a nutshell. You should be able to understand it. I put it in the table here. But for today's lab, we are using a cool reaction of cobalt chloride, right? Cobalt chloride bound to water. This is a nice compound that you have, and it changes color. That's the beauty of this lab, is we're going to be seeing a color change so that we can visually see how we are affecting the equilibrium. So cobalt chloride, right, turns into chloride, free chloride ions, and this nice compound right here, right? Cobalt 2 plus hydrate, right? So it's a cobalt ion bound to water. The beauty of it is, like, the cobalt chloride, this one is blue, this one is kind of like purple pinkish, right? And then you have in between. So you have the color for the product, the color for the reactant, and then the color for the product, so we can monitor how one goes into the other, right? And we're going to do that. We are going to shift the equilibrium, and that's what we're going to do, right? Because guess what? If you take this, right, and then you add chlorine, for example, if you add chlorine, which is the product, where do you think it's going to shift to? If you add the product, it's going to shift that way, right? It's going to shift this way. If you add the product to a pink solution, it's going to shift that way. So if you have pink, you add product, it's going to go to blue. And guess what? If you add water, right? If you add water, because water is in here, is the reactant. If you add water, it's gonna go that way to get rid of it. So water is in the reactant, and cobalt chloride um, is in the product. So we're going to try both. We're going to try both. We're going to add water. So we're going to add water to bring it here, and then we're going to add chlorine to bring it back here. That is the equilibrium, checking equilibrium based on concentration of the product and the reactants. And guess what? We're going to do the same with temperature, because this reaction also changes color based on temperature, right? So if you increase the temperature, it should be blue. And then if you start to decrease the temperature and put it on ice, you will see it turn back to pink. It's really cool. So we are going to do two experiments, two equilibrium experiment, one concentration based, one temperature based, where for the concentration based, we're going to to add the reactant first, and then we're going to add the product, and then for the temperature based, we're going to cool it down and then heat it up. So we're going to use hot water, we're going to use ice, then we're going to use room temperature, and we should see a nice color change based on equilibrium. So I think that's all you need to know. I think you understand very well what we need to do. So if you're ready, let's get started.
In this lab, you're gonna need 3 chemicals. You're going to start with our main chemical, which is cobalt chloride, which is in a brown bottle. You should also have your water, the ionized water, and you should have concentrated HCl in a dropper bottle. You should also have a waste container to dump all your cobalt chloride in. We will not put this into the sink. In addition to that, you should have 2 beakers as well as 4 test tubes on a rack. We're going to use this in our experiments. In addition to this, we should have some sort of temperature control. So we should have a hot and cold temperature control. The hot should be like an ice container. No, the cold should be a ice container, and the hot should be just a container with hot water. And of course, you're gonna have your gloves and goggles. And after you have everything, you should be ready to get started. And to get started, we're going to start by putting on our gloves and goggles like we see here, making sure that we have everything, making sure that everything is good to go. And after we put on our gloves and goggles, we are ready to get started. In order to get started, we're going to start by part 1 of the experiment. The part 1 of the experiment starts by adding our cobalt chloride into the solution. So we're going to start to add our cobalt chloride into our tubes using a dropper bottle. Right? So you're going to go ahead and add about, I believe, 3 milliliters. No, about 1 milliliter. And again, 1 milliliter is about 25 drops of liquid. So you're going to add enough as shown here, and then you're going to perform the first experiment by adding water into that mixture, right? So we're going to start our first experiment by changing the concentration of two things. Number one is water, number two is our chloride ions, right? So basically we're going to add a product, and then we're going to add a reactant, and then we're going to see where our reaction shifts to. Why do we like this? Is because when the reaction shifts one way, it turns pink. When it shifts another way, it turns blue. So you're going to perform the experiment with both the acid and water to see where it shifts to. If you don't see the effects, just keep adding, and you should see either the reaction turning more pink or more blue depending on what you're adding, right? For example, here we added acid, I believe, in here, and then when you add acid, your reaction should turn into more blue. So as you can see on camera, the reaction turns more blue when we add acid. So we're adding Cl minus ions and shifting our equilibrium. And after you're done with changing the concentration, we're going to go to the next experiment where we are going to change our temperature. In order to change our temperature, we're going to have 3 tubes. So in our 3 tubes, we're going to add our cobalt chloride in the 3 tubes, right? And then after you fill the 3 tubes, as indicated, you are going to now have them at different temperatures. So here we're not going to add anything. You just have to put one at the cold. So as you can see, we're setting up 2 beakers. One beaker contains ice with a little bit of water. The other beaker contains hot water. So you bring your hot water, you bring your beaker with ice water, and then the other one is going to be at room temperature. So we're going to take our 2 samples, we're going to dump them into the 2 different temperatures. If you're feeling more adventurous, you can also go ahead and put them into check the temperature. You can go ahead and check the temperature of the water. But as soon as Bryson here puts our tubes in ice and hot water, you can see them changing very quickly. When you put them in ice, they become more pink. When you put them in hot water, they become more blue. And that is very clear. We have not added anything else. We just changed the temperature. And we are showing experimentally that when you change the temperature of a reaction, it's going to shift one way when you heat it up, and then it's going to shift one way when you cool it down compared to the room temperature. And those are the 2 main experiments when it comes to equilibrium. One looking at when you change the concentrations of both the reactants and the products, and then the second one looking at the change in temperature both going up and going down. So we have looked at 4 different changes in concentration. And as I said before, after you're done, make sure that you dump all your cobalt waste into a waste container, a dedicated waste container. And after that, be careful with steel gloves on to rinse everything in the sink, clear your desk, and put everything back. So cobalt chloride is dangerous and hydrochloric acid is dangerous. So make sure that you don't touch it. Don't let it get in on your skin. Don't test it. Don't play with the chemicals, because safety is number 1. But other than that, you are done. You are good to go.
Okay, that was equilibrium. I hope you liked it. Make sure that you fill out all of the data sheets, pre-lab, post-lab. And if you have any questions, feel free to reach out. And I will see you in the next lab. Bye bye.